So hello everyone and welcome to my presentation on my master thesis, which is called Exploring the Effects of Conditioning Independent Q-Learners on the Sufficient Plan Time Statistic for Dec-POMDPs. This was done with my mentors Frans, Oliehoek and Aleksander, Czechowski. So in my thesis I investigated the decentralized partially observable Markov decision process, which is a more complex form of the regular Markov decision process, which is commonly used in reinforcement learning. So in the decentralized partially observable Markov decision process, which I'll just refer to as a Dec-POMDP from now on, multiple agents must cooperate under partial observability using local information. So a common example of this would be self-driving cars, where each of the cars has some local information, what it sees itself, but it must then reason about, what do the other cars see? What are their goals? How do they want to achieve these goals? So there's a lot of uncertainty in these environments. So what makes these Dec-POMDPs so challenging is first of all that the true state is hidden, and instead the agents receive noisy observations about the state instead. This is very common in these partially observable Markov decision processes. But moreover, there are multiple agents, and most importantly, the execution is decentralized, which means that each agent only knows the actions it's taking itself, so it has no knowledge about the actions that the others are taking at the same time. And moreover, each agent only receives its individual observations, and it has no knowledge about the observations that the others are receiving. And these are formally known as each agent maintains an individual action observation history, which I denote with this Greek letter theta. So compare this to your more simple Markov decision process, in which a single agent acts in an environment in which the true state is also fully observable. And you can sort of get a glimpse of why this Dec-POMDP might be so challenging. So a common way to address these multi-agent scenarios is independent Q-learning. So in independent Q-learning, each agent learns an individual action value Q function. So what this means is that each agent maintains sort of this mapping from individual action observation histories to the value of actions. And they do so by, you have this old estimate, and then after you actually take this action, given this specific individual action observation history, you receive a reward, which is this RT on the right side. And then based on this reward, you update your old estimate. You either increase the value or decrease the value based on, what was the actual reward I received when I actually took this action in the environment. And you can see how these independent Q-learners, so the idea is that each agent concurrently but independently performs these updates rules. So you can see why this is easily scalable, because it only considers local information. Each agent only learns a mapping from their own action observation history to the value of their individual actions. But of course, this also comes with many problems, because the actual reward clearly depends on the joint action, right? So it does not simply, the value of an action does not simply depend on, what was the action I took, but it also depends on, what were the actions that the other agents took at the same time. So in a way, these independent Q-learners are completely oblivious to the presence of other agents. And as a result, it is shown that independent Q-learning is likely to converge to a Nash equilibrium. But there is no guarantees about the quality of such a Nash equilibrium. It certainly does not have to be the optimal. So in a Dec-POMDP, agents make these decisions based on their individual action observation history, because really that's all the information that they have access to during execution. But the value of an action, like I just said, clearly depends on the actions that the other agents are taking at the same time. So ideally, an agent should make decisions not only by using their individual action observation history, but also by sort of reasoning about the action observation histories that the other agents might be experiencing or might be in right now, such that they can then predict what the other agent might do and then adjust their own behavior accordingly. So this is sort of where the sufficient statistic for Dec-POMDPs comes in. So the sufficient statistic is formally defined as a posterior distribution over state and joint action observation history tuples, based on the policy that was followed thus far. So I denoted it with this sigma t, and well, this definition is precisely what I just described. It's the probability distribution over state and joint action observation history tuples. So our idea is, well, what if we condition these independent Q learners on the sufficient statistic to learn this Q value that, not only maps individual action observation histories to the value of actions, but also depends on this distribution over the joint action observation history. So in this way, by conditioning on the sigma, the agents have knowledge about the private information that the other agents might be experiencing. And this is precisely a way to combat sort of the obliviousness of IQL, of independent Q learning, to the presence of other learning agents. Because now they actually take into account, well, what could be the information that the others have, and what might their resulting actions be. And then they can more accurately, adjust their own behavior. So this is sort of the overview of our learning setup. So we train two agents independently and concurrently, as is traditional for independent Q learning. But the most important thing is that we not only use the individual action observation history, but we also condition on this sufficient statistic. And the agents use a deep Q network to then learn the value of actions, given both. So given both the individual action observation history and the sufficient statistic. So the main research question we sort of investigated is, well, can these independent Q learners escape suboptimal equilibria by conditioning on the sufficient statistic? And like I just said, we hypothesize that through the sufficient statistic, agents will be able to more accurately predict the actions of others, so they will be able to learn better final policies and hopefully escape suboptimal equilibria. So our findings. So, well, first of all, agents must explore in the space of entire decision rules. A decision rule is simply a lookup table matching observation histories to an action. So a decision rule for time step t simply enumerates all possible action observation histories at time step t, and then for each of those it maps them to a specific action. So the reason agents must explore in the space of these entire decision rules is that the sufficient statistic can only then distinguish exploratory actions from greedy actions. And as a result, through the sufficient statistic, agents can then communicate their exploration. I don't have time to go into the details, unfortunately, but compare this to, commonly agents simply explore in the space of individual actions, right? For example, we're using epsilon greedy. With probability epsilon, they take a random action, and with probably 1 minus epsilon, they take a greedy action. And we found that by conditioning on the sufficient statistic, when you actually explore in the space of actions, the sufficient statistic cannot distinguish between exploratory and greedy actions. And as a result, it provides no useful information for escaping suboptimal equilibria. So agents must really explore in the space of these entire decision rules. So what this means is when they explore, they now form a completely random decision rule, so which maps each possible action observation history to a random action, and then simply they take the action that is prescribed for their specific action observation history. So in a way, the sufficient statistic can then communicate their exploration. So one agent now knows through the sufficient statistic when another agent has explored. And this is key for escaping the suboptimal equilibria, right? Because when you explore individually and the other doesn't, by the very definition of a Nash equilibrium, the reward you receive will always be worse than if you simply took, the action corresponding to the equilibrium. So the agents must really coordinate their exploration such that they explore favorably at the same time. And this is very important to escape the suboptimal equilibria. And this is precisely why we condition on the sufficient statistic, because agents can then communicate their exploration. Secondly, So while the sufficient statistic communicates exploration, recall that it summarizes only the history of joint decision rules. But to escape a suboptimal equilibrium, agents must really coordinate their exploration at the current time step, right? So the sufficient statistic is insufficient because it only considers how have we explored in the past and not how do we explore at the current time step. So in order to solve this, we additionally sequence the decision making during learning. And in this way, the agents can then distinguish between exploratory and greedy actions of others at the current time step. So what we did is by sequencing the decision making, the agent that is, for example, last to ask, additionally conditions on the current decision rules of the earlier agents. So when the earlier agents now explore to a random decision rule, the final agent will then see through by conditioning on these earlier decision rules, okay, so the earlier agents are now exploring, so I should also perhaps explore, or I should still act greedily. And then by being able to distinguish between exploratory and greedy decision rules of the earlier agents, the later agents can adjust their own behavior accordingly. And what we found is that by conditioning on the sufficient statistic and also by conditioning on the current decision rules of the earlier agents, these agents were really consistently able to escape suboptimal equilibria and learn the optimal policy. So in this graph, so we ran 50 iterations of the same experiment. So each line represents the reward achieved for the iteration. And you can really see that initially most of the runs are stuck in the suboptimal equilibria, right? Receiving an average reward of -20 or -10. But as learning progresses, each of them manages to escape the suboptimal equilibria and find the optimal policy with a reward of about 5. So this is the Dec-Tiger environment for Horizon 3 for those interested. So this was my presentation. Unfortunately I don't have too much time to go into too much detail, but if there are any questions, I'd be happy to answer them in the upcoming Q&A session.